for that. So, all right. Today we're going to learn a new lesson, kind of. Well, no, it's a new lesson. The reason I say kind of is because there's an aspect of it that we have already talked about, and the more you see this, the more it kind of it gets a little simpler the more we do it, and that is the transformation. See, today we're actually talking about exponential functions for the first time, okay? It's a new unit. I had already kind of told you that we were finishing a unit with that last inverse functions note sheet, and instead of testing, since there was only two things that we covered after we got back from Christmas break, we are ready now to move into a new unit with new material, and that material is going to start with exponential functions. Now, the reason that I tell you that it's stuff that you've seen before, that's because we just graphed radical equations, and when we graph those radical equations, we talked about these things called transformations, and these same transformations are going to be applied to what we're doing today. So there's some very similar things that we're going to include in today's lesson that we've just done recently. Okay, so that's kind of the neat part of it. It's not going to be all that difficult because it's stuff that you've seen before. So let's go ahead and get started. Let me check roll real quick. It's what do it? Yeah, it's the 20th. Time flies when you're having fun. Y'all don't have to laugh so sarcastically. I mean,
are you recording?
Y'all's laugh's not that hard. Yeah, it's recording. So here's all the things that you might say to me that would be mean and rude.
And all the threats.
Yeah, you make a lot of threats.
Yeah, you do make a lot of threats.
Y'all are just saying that because of the video. And y'all want it to be in the video.
Yeah.
Alright, anyways, let's go ahead and get started, you little babies. Alright, so today we're talking about exponential functions. And in the past, we've done functions that have exponents in them. Okay, quadratics have exponents, don't they? Quadratics is x squared, right? Well, I know it has an exponent. That's not what makes it exponential. What makes an exponential function is the variable is in the exponent spot. Okay? That's what makes it an exponential function. The variable is in the exponential spot. Just because a function has an exponent, that's not what makes it exponential. What makes it exponential is the variable is in the exponent spot. So here's what your parent function will always be. F of x equals some base raised to the x power. Okay? And there's a couple things that you need to know about b. One, b has to be greater than 0. Alright? Now you might have a negative attached to it, but it's going to be the a value which causes it to do a specific transformation that you guys are probably going to be relatively familiar with. But the actual base of your exponent has to be a positive number. Okay? Now, secondly, it cannot equal 1. B cannot equal 1. I mean, think about this. When we do exponents like this, if that base was a 1, what's 1 raised to any exponent in the world? Remember, raising it to exponent means you multiply by itself. If I keep multiplying 1 by itself, what will it stay? It'll stay 1. So if I tried to graph that, it wouldn't be exponential at all. It would just be a horizontal line, not an exponent. Okay? It wouldn't be an exponential graph at all. So b cannot equal 1. So there are two options, okay, for that value of b. That value of b could be greater than 1, or it could be less than 1. If that value of b is greater than 1, then our graph is going to have what we call exponential growth. It's going to have exponential growth. And if it has growth, it's always going to be increasing. Y'all with me so far?
Yes.
Now, if b is less than 1. And again, just remind me, what are some values that are less than 1 that we could actually put in this category? 1/2 would be less than 1, right? 1/3, 2/3. Those are values that are less than 1. If that happens, it doesn't have exponential growth. It has what we call exponential. Anybody heard this before? Exponential
Decrease.
close. Exponential decay. It's called exponential decay. I know most juniors have chemistry. This is going to be something that you're probably going to talk about in that class, exponential growth and decay. So you're kind of getting a head start on it now. You will see it, okay, when y'all start talking about stuff like bacteria or whatever. I think y'all cover that in your chemistry class. You're going to see exponential growth and decay even in that class, okay? Now, if it has decay, what do you think it's going to be doing over the course of the graph? It's going to be decreasing. There's going to be a lot of similarities between these graphs, but there's going to be a couple of obvious and vast differences too. And we're going to look at a graph of both of those here in just a second, so bear with me. But we got to learn about this one other term that we start seeing, and the first time you've seen it is right here in exponential functions. Now you're going to see this, possibly in your class next year if you take pre-calculus, which I think a couple of you guys should do. You should consider taking pre-cal. A couple of you guys, probably would want that challenge. Plus, it would absolutely help you with your ACT score to take pre-cal next year. Well, when you get to pre-cal, you're going to find out there's other types of these, but the term is called asymptotes. Okay, you can have different types of asymptotes. You can have horizontal asymptotes. You can have vertical asymptotes. But what an asymptote is, it's a line that a function will approach but never touch. It's like a barrier, okay? An undrawn, unseen barrier. In fact, in pre-calculus, a lot of times people will label their asymptotes with dashed lines. So when they're graphing it, they know that they can't go past that asymptote. That your graph will approach it, but it'll never cross it or touch it, okay? We don't generally draw the horizontal asymptote that we're going to have, and I just kind of gave away the next thing I'm going to tell you, but we just know where it's at, okay? But that's the second thing. When it comes to exponential functions have horizontal asymptotes. Exponential functions have horizontal asymptotes. So I want you to write one more thing. After you write that, over here underneath this asymptote, I want you to put y equals 0. Y equals 0. And we'll talk about this in just a second. But every one of our exponential functions is going to have a horizontal line that graph will approach it, but it will never cross it. It makes graphing these pretty simple, as we'll look at in just a second. There is something in particular that will change our horizontal asymptote. And we'll talk about that in a little bit. But the first thing I want you guys to understand is, in the most basic representations, our parent functions, if you will, for all exponential functions, your horizontal asymptote is y equals 0. Now let me explain that. The reason it's y equals 0 is because it's the x-axis. The x-axis is your horizontal asymptote for all of your parent functions for these exponential graphs. Now, there's one thing in particular that changes that asymptote. But in its most basic form, the horizontal asymptote is y equals 0. Because the x-axis and all horizontal lines, they cross what axis in common? All horizontal lines cross what axis? The y-axis. And since all horizontal lines cross the y-axis, we name horizontal lines by where they cross the y-axis. Does that make sense? That's why the x-axis, we would call that horizontal asymptote y equals 0. Because where does the x-axis cross the y-axis? At 0. Does that make sense? Are y'all following me? So the reason I want you to put that y equals 0 right there underneath that asymptote is that's your basic asymptote for a parent function for all exponential functions. There is one thing that will change that, but it'll make that change to y equals 0. Okay? And we'll talk about that in just a minute. But before we talk about that, I'd really like to go and look at a couple of graphs. I want you to make a quick change to number 2. I want to do one that's exponential growth, and I want to do one that's exponential decay. So we're going to leave one alone. We're going to leave that 2 to the x. I'd like you to change number 2 to 2/3 to the x. 2/3 to the x. If y'all would make that change for me, I'd appreciate it. We're going to graph that in a second. I want to see one that's exponential growth with you and one that's exponential decay. Okay? That way we can compare the differences between the two. Let's start with the exponential growth. What's up, Deanna? You okay?
Yeah.
Alright, so I would recommend you reset your calculator. It's always a good thing when people have messed with them. Where do we go when we want to graph? Where do we go? We go to y equals, okay? Y equals, and we're going to type our 2 in, and we're going to raise it to the x. Again, I want you guys to notice a couple things. This is just a very basic exponential function, and it has 0 transformations. 0. We'll talk about the transformations next, but it has 0 transformations on it so far. So this is going to be a very basic exponential what? Growth. Very good. It'll be a very basic exponential growth function. So let's see what it looks like. All right, I want you guys to notice something. Y'all see how it never crosses the x-axis? It's approaching it. It never crosses it. If that graph, if we kept extending it out to the left, or even look at this, go to your table. If I just kept on going to the left, look, x equals negative 15, x equals negative 20. These values right here are getting closer and closer and closer and closer and closer to 0, but guess what it will never do? It'll never cross the x-axis. It'll never cross it. So, therefore, my horizontal asymptote here is y equals 0. All right, we'll talk about that in just a second, but I want you to first of all find a couple of points that we can graph. Y'all see some good ones? This one's important. When your x value is 0, your y value represents where it crosses your y-axis. So 0, 1 is what we call our y-intercept. Okay? You always find your y-intercept where x equals what? You always find your y-intercept where x equals what? 0. Very good. All right, so let's talk about this real quick. Let's find some points and plot them. I'm going to plot a point at the y-intercept, 0, 1. There's some other good ones. 2, 4 is a good one. You can put as many of these as you want. I'm going to go ahead and put 3, 8 as well. So I'm only going to do 3 of these points on my graph. And I'm going to graph this with some pretty easy confidence, knowing it can never cross what? The x-axis. So I'm going to draw this thing to where it's just hugging that x-axis, and it's starting to increase gradually until it starts making its real turn upward. And that is what exponential growth looks like. What do you think? Is that hard to graph? All right, so let's talk about some terms. For all exponential graphs, right now we're talking about exponential growth. Will it ever be limited to the left and right? Will this graph ever stop going left? Will it ever stop going right? So my domain is always going to be unlimited. How do I state an unlimited domain? Negative infinity to positive infinity. Okay? But how about range? Is the range limited? Yeah, remember there's an asymptote. It never allows you to graph below what y value? 0. I can never go below this point. So y can only be the values from 0 and up. How do I state from 0 and up?
You put a bracket.
Wouldn't it be a bracket?
Okay, good question. In some of the ones we've done in the past, it is a bracket. The reason this one's not a bracket is because does this graph ever get to 0? No. It always goes towards 0, but it never quite gets there. Since it never quite gets there, you can't use a bracket, you use a parenthesis. We use a bracket when it actually gets to a specific value. But if it's just approaching that value, you have to use a parenthesis. So in this case, it's a parenthesis at 0. It's just like infinity. Can I ever get to infinity? No, I'm always just approaching infinity. And that's why we always use parentheses for infinity. Same with 0 here. We're approaching 0, but we never quite get there. Yes?
So does the 0 have to be like on the y-axis, or could it be anywhere on the x-axis? Or is it just 0 as in the point 0?
Okay.
That's probably different.
No, it does. I know the question is, I think, is about the y value being 0. Is that what you're saying?
Yeah.
See, remember, even though it's way over here, the y value, to get to that point, it can never quite be 0. It'll always just be fractionally bigger than 0. Okay? So it's the point 0. Not here, but way over there. Okay? But it's still, this is the barrier it can't get below on the y-axis. That's why your range is limited to 0. Does that make sense?
Yeah.
We might be asking a different question than what I'm answering. All right, let's do the next part, in behavior. Now look at this, guys. As my x value goes off to the right, which way is y going? It's going up. And will it keep going up and up? So what's it going to always approach as x goes off to the right? Infinity. Now again, look at this next one though. As x is going off to the left, what's y approaching here? What's y approaching? 0. Remember, it's always approaching the asymptote. So my end behavior is unlimited in one direction, limited in the other. Okay? Does that make sense? That's pretty easy, hopefully, concept. And then, of course, the last two we already got. What do we say the y-intercept was? Where does it cross the y-axis? At 0, 1. We'll name it as an ordered pair. 0, 1. And then finally, what do we say the asymptote is? Y equals 0. Y equals 0. That's the x-axis. Okay? So this is what the function looks like. This is what the graph and all those terms look like. Let's look at the other direction and see what changes. Okay? And when I mean the other direction, I mean a vertical or a exponential what? Decay. All right, so let's go to our graphing calculator. Let's clear that out, and let's change it to instead 2/3 raised to the x power. Again, the base of your exponent here is a value less than 1. So this one's going to show exponential decay. So sure enough, is it decreasing over the life of the graph? Absolutely it is. Okay, a couple of things. Does it ever go below the x-axis? No, so my horizontal asymptote is still what? Y equals 0. Okay? Any parent function of an exponential graph will not go below the value y equals 0. There is one thing that changes that, and like I said, we'll talk about that in just a second with transformations. All right, so let's find a couple of nice points here. Second graph, to look at my table, and I need y'all's help here. If y'all notice, there's no really nice number. So y'all help me find this one. Right here, -5, 243 over 32. Somebody type in your calculator, 243 divided by 32. 243 divided by 32. 7.6? All right, so let's go to -5 on our graph. And then go up to 1, 2, 3, 4, 5, 6, 7.6. 7.6. And again, just get as close as possible to 7.6. Okay, I'm going to keep scrolling down here. Somebody tell me what 9 divided by 4 is. 9 divided by 4. 2.25. So go left 2, and then go up 2.25 and put a dot. And then we got a nice point right there at 0, 1, right? Which is our what? That's our y-intercept. Very good. So let's go graph this thing now. I got my points already drawn. Hopefully yours are pretty close to the same spots. They should be pretty close. And I'm going to draw this graph to come through those points and then never do what? Never touch the x-axis. So it's going to curl and just hug that. It's going to hug that x-axis. It's going to get so close to it, it looks like it's touching it, but it never touches it. Okay? It's called an asymptote. It cannot touch that horizontal asymptote. And in every basic graph with no transformations, that asymptote is y equals 0. All right, now, you can tell there's a major difference between this graph and the other one. It's clearly going down from left to right, correct? So a major difference. But look at all the similarities. If I said, what's the domain? Guys, does this thing ever stop going left or right? So just like above, what's my domain? Exactly the same domain. Same with range. Does this thing ever go below the y value of 0? Does it go above the y value of 0? So it's going to be all values from 0 to infinity. The y-intercept for this graph was still what? 0, 1. Because it had no shift, no change. We'll talk about that later, I promise. I keep saying we'll talk about this later. We are. We're getting it. And the asymptote is still what? Here's the only thing that changes. And it does one major thing. It doesn't just completely change. It just flips. Let me explain. As x goes off to the right, what's y approaching? 0. But as x goes off to the left, what's y approaching? Infinity. So it actually is the same answers as the one above it, just flipped. So there's so many similarities between these two graphs. The major difference is one's going up from left to right, one's going down from left to right. Exponential functions can be growth or decay. And you see them here, okay? Now, here's the part of this lesson where it should be so familiar to you guys, it's not even funny. Because we literally just talked about graphing radical equations, and there were how many transformations? How many transformations were there? 4. And how many locations did those transformations happen? 3. It happened in 3 places. Let me explain. Okay, look guys. If you look right here, b is the base of your exponent. If there's some value out in front, like a negative or another number, that is going to be your a value, and a controls how many things? 2. 1. What if it's negative? If a is negative, what does it do to your entire graph? It reflects it over the x-axis. Is this the first time you guys are hearing this? No. It's the same thing that happened with our radical equations. The same thing that happens with our quadratics. If your a value is negative, it reflects it over the x-axis. Same. Okay, next. What if that a value is greater than 1? What does it do to your graph? It vertically stretches it. Again, that's not the first time you've heard this. But what if that a value out front is less than 1? Between 0 and 1. It vertically what? Compresses. So a controls 2 things. Reflecting, and if it's any value other than 1, it vertically stretches or compresses based on what the value is. Next, what if something is being added or subtracted inside? But inside in exponential functions mean in your exponent spot. If something's being added or subtracted in your exponent spot, that is representing a horizontal shift, just like it did with radicals. Okay? It's just about location. And what did we say about horizontal shifts when they're happening inside? It's the opposite. So if this says minus h, h is actually going to be positive horizontal shift to the right. But if that said plus h, it's actually a negative horizontal shift. So it would go left. So positive means left, and negative means right. And then finally, you have that value on the outside at the very end of your exponential function that's being added or subtracted, and it represents what kind of shift? Vertical. We've talked about every single one of these, and we said that vertical shifts are what they are, right? It is what it is. So if it's positive, it's going to shift up. And if it's negative, it's going to shift down. Okay, last thing before we talk about a couple of these examples. What was that new thing that we talked about with exponential functions? A weird word. Asymptote. And we said for all parent functions of an exponential function, your asymptote is located where? At y equals 0. It's a horizontal line. We call it the x-axis. Y equals 0. Out of all those transformations, which one's going to change your horizontal asymptote, you think? Out of all those transformations we just discussed, which one's going to make that horizontal asymptote move? Nope. Nope. What would make that horizontal asymptote go up or down? Your vertical shift. Your k. Your k value changes your asymptote. So I would like you just to add that in your notes. Changes asymptote. That is what changes your asymptote. If it vertically shifts up 3, your asymptote is going to go from y equals 0 to what? Listen to me one more time.
Y equals 3.
Exactly. Did y'all hear that? If your asymptote shifts up 3, if your exponential function shifts up 3, it's going to change from y equals 0 to y equals 3. if your exponential function shifts down 4, your asymptote will change from y equals 0 to y equals negative 4. Your k value is what changes your asymptote. Okay? So that'll help me when I start graphing these things. I'll know the barrier that I can't draw my graph past. I'll find my points using my calculator, but I'll know I can't go past that k value. That's my asymptote. Okay? If it's not there, if I have no k value, my asymptote is y equals what? 0. Okay? So let's talk about these real quick, and then we'll call it a day. Now, it says identify the parent function. And that's the unique thing about exponential functions. Your parent function changes. And the parent function is simply what is the base of your exponent. So in this case, your parent function is just what? 3 to the x power. Does that make sense? Look at number 3. What would be the parent function of that one? What is just the base of your exponent? 4/3 to the x. Over here on number 2, what's just the base of your exponent? Just the base. Just the base of it. On number 2. Nuh-uh. 1/4. 1/4 is just the base. On number 4, what is just the base of your exponent? Nuh-uh. That's your a value. 5. These are our parent functions for all 4 of these. Any change to this is representing a change, a transformation that we've talked about. So for example, look at number 1. What's the only change to that? That plus 5, right? And where is it happening? Is it in the exponent spot? No, it's outside, being added 5. So what kind of transformation is that? It's a vertical shift. And vertical shifts, they are what they are, right? So if that says positive 5, it's going to shift how? It's going to shift up 5. Look over there at number 2. What changes have been made from that parent function, 1/4 to the x? Well, there's an a out in front, isn't there? Is it negative? So no what? No reflecting. But is that a value greater than 1 or between 0 and 1? So it's going to have a vertical stretch. A vertical stretch. What other changes happen to that parent function? Well, I'm subtracting 1 in the exponent. In the exponent is horizontal shift, right? And it's the opposite. So if that looks like a -1, it's actually a positive 1 horizontal shift. What is a positive 1 horizontal shift? Shifts right 1. I hope y'all are understanding this. I feel like I'm having to answer more than usual with you guys. Look at this one. Parent function. What changes were made? There's a negative. It reflects across the x-axis. There's also a +2 in the exponent. That's horizontal shift. And it's the opposite. So it's actually a -2 horizontal shift. What's that mean? Shifts left 2. And then finally, there's also a vertical shift. It is what it is. So this one's going to go up 7. 3 transformations in that one problem. Okay, look over there at number 4. The base of your exponent was just 5. So 5 to the x was your parent function. What changed? Well, there's a 1/2 out in front. So that's going to be a vertical compression. You got that -4 in the exponent. That's a horizontal shift. It's the opposite, so it's actually a +4 horizontal shift. What's that mean? Shifts right forward. Very good. And then finally, you got that -2 outside. That's vertical shift, and it is what it is. So it's going to do what? It's going to go down 2. And that's how you recognize your transformations. Listen, they're so much like radical equations, it's not even funny. Okay, we've done this. So don't let it get you puzzled now. It's the same things we just did. It's just with a different type of function. Now, last thing, real quickly, before we look at that last graphing example. How many of these did the asymptote change? How many of these did the asymptote change? 3? Then I should ask a better question. Did that have drink in it? Oh, good. It wasn't open. Which one did not change the asymptote? Are you sure? It'd be number 2.
Oh, wait.
Number 2. Because look, what did all of them do except for number 2? A vertical shift. So, real quick, and you don't have to graph this. What would be the horizontal asymptote for number 1? Y equals 5. 3?
Y equals 7.
Y equals 7. 4?
Y equals 2.
I guarantee you, if you graphed any of those 3, you would see that whole thing shift to those locations. This one would shift to 5. Your graph would approach 5 and never touch it. It would just hug it. This one would approach 7 and never touch it. This one would approach -2 and never touch it. Okay? And then that one, number 2, would approach what? 0. Very good. Okay. So, last thing, let's do a quick graph here. And this one is so very similar to number 1, the first graph we did. The only change it has is it did what? It shifted to the, where's that shift happening? Left 5, right? Because it's inside the exponent spot. So it's the opposite. So it's a horizontal shift left 5. Let's graph it and see what happens. Y equals, clear that out. I got 2 raised to the, raised to the x plus 5. And sure enough, look at the graph. Y'all see how it shifted left 5? But still, what's it approaching and never crossing? 0, because it didn't shift up or down. So I'm going to find a couple of quick points. I like -5, 1. That's a good one. I like -3, 4. You don't have to do all of them that you see. Just do a couple of them. And then I like -2, 8. Before we turn off of this, is everybody looking up here? I'm not going to be graphing the y-intercept, am I? But what is the y-intercept? Remember, look at your table for your y-intercept. Your y-intercept is wherever x equals what? So your y-intercept is going to be way up at 32. I'm not going to be graphing that. My coordinate plane doesn't go that high. But you know that your y-intercept is 0, 32. Okay, so let's go finish this thing up. Your graph should look similar to mine. It approaches the x-axis, never crosses it, goes through all my points. It's going to go on up off the graph. Now, look how easy this is. Go back to your first examples. What's your domain? Your domain always? Negative infinity to positive infinity. Guys, did my asymptote change here? Then what's the lowest point on y that it could go? 0. If my asymptote changed, my range changed. Y'all know that, right? In behavior, as x goes to the right, what's y doing? Going up, just like all exponential growths will do. And then, of course, you've got, as x goes to the left, it's approaching the asymptote, 0. We just said that the y-intercept is 32, 0, 32. And we said the asymptote did not move. So, boom, there you have it. Okay? So, fairly simple. Your homework is coming now. Let me apologize. The actual printout, the front side got real, I don't know what happened to make it all dark and faded like this. I apologize. I don't know why I did that. I know. So your homework, y'all ready? Is numbers 1 through 5. And then 6, 8, 10. So I guess technically I could have said 1 through 6 and then 8 to 10. So 1 through 5, 6, 8, 10. Do tomorrow. Tomorrow we're going to, being Thursday and all, last day of our week, we're going to solve these exponential equations. All right? So we'll go over a couple of these, and then we'll jump in to that new lesson tomorrow. Okay? I'm going to go ahead and close this since it's the lesson, and y'all can utilize this time to use your graphing calculators, hopefully, to finish this thing off.